For an object in xyx space with a temperature defined by the function T of xyz, the heat flow is defined as F equals negative K times the gradient of T. K is a constant called thermal conductivity and is a physical property of the material the object is composed of. The rate of heat flow across surface S is calculated by the flux integral given by the double integral of F dot ds equals the double integral over the surface S of negative K times the gradient of T dot ds. We have a solid hemisphere given by the inequalities x squared plus y squared plus z squared is less than or equal to 25, and z is greater than or equal to 0. This means we're looking at the hemisphere of radius 5 that is above the xy plane. The temperature at point T of xyx equals 1 half x squared plus 1 half y squared plus 1 half z squared. We are also given that K equals 80 for this problem. The heat is given by the flux integral across S of negative K times the gradient of T dot ds. The gradient of T equals xyz. We get this from taking the derivative of each component. Notice that S is a piecewise smooth because it is composed of a circular bottom, S sub 1, and a spherical top, S sub 2. We need to calculate the heat flow for each piece and sum them up to get the total heat flow. Let's start with the bottom, which is a circle centered at 0, 0, 0 with radius 5. Therefore, it makes sense to parameterize in polar coordinates. This gives us the vector r of u v equals v cosine u, v sine u, 0, from u between 0 and 2 pi and v between 0 and 5. It follows that the tangent vector t sub u is negative v sine u, v cosine u, 0. We also have t sub v equals cosine u, v sine u, 0. Finally, t sub u cross t sub v equals 0, 0, negative v sine squared u minus v cosine squared u. Simplified, this is 0, 0, negative v. This makes sense because the normal vector should be pointing straight down. Next, we set up our integral. Substitute in 80 for k in the limits on the integral. The outer integral with respect to u will go from 0 to 2 pi, and the inner integral with respect to v will go from 0 to 5. Plugging in our previously calculated vectors, we get negative 80 times the integral from 0 to 2 pi of the integral from 0 to 5, v cosine u, v sine u, 0, dot product, 0, 0, negative v dv du. Since the dot product evaluates to 0, this whole integral equals 0. The second piece is the top, which is a hemisphere centered at 0, 0, 0 with radius 5. Therefore, it makes sense to parameterize in spherical coordinates. We'll let u be between 0 and 2 pi, and v be between 0 and pi over 2. This gives us the vector r of u, v, equals 5 cosine u sine v, 5 sine u, sine v, 5 cosine v. It follows that the tangent vector t sub u equals negative 5 sine u sine v, 5 cosine u sine v, 0. It also follows that t sub v equals 5 cosine u cosine v, 5 sine u cosine v, negative 5 sine v. Finally, t sub v cross t sub u equals 25 cosine u sine squared v, 25 sine u sine squared v, 25 sine v cosine v. We took v cross u to make this vector positive. Next, we set up our integral. Substitute in 80 for k and the limits on the integral, u from 0 to 2 pi and v from 0 to pi halves. Plugging in our previously calculated vectors, we get negative 80 times the integral from 0 to 2 pi of the integral from 0 to pi over 2 of 125 sine v dv du. Factoring out constants and integrating with respect to v, we get negative 10,000 times the integral from 0 to 2 pi of du, which equals negative 20,000 pi. Finally, s equals s sub 1 plus s sub 2, which equals 0 minus 20,000 pi, which is negative 20,000 pi.